everybody to the UMN Robotics RI3D Robot in 3 Days robot. This is Poseidon, our robot for the year. We began constructing this robot on Saturday at about 12 p.m. And the general design process we took was to spend about the first 2 hours mapping out 2 different design visions for the robot and choosing one of them to pursue. And then we split up into a bunch of different design groups to both prototype, come up with different ideas, think through things for all of the different mechanisms on this robot. And what we came up with was this final product. This robot is designed particularly to score coral on all 4 stages of the reef. It is made to be able to knock algae out of the reef. It is made to be able to intake algae off the ground and score it in the processing station. And we designed it such that it would be able to climb on the shallow cage. That now we'll talk about later that didn't end up being fully implemented, but capabilities that this robot is not able to do is it is not able to climb on the deep cage and is not able to shoot coral and shoot algae up into the net at the top of the main bay there.
Alright, here's our intake subsystem. So when we came up with those designs at first, this was the initial geometry we came up with. It keeps the algae compressed in our inside our chassis so that we can just roll it out into the processor. It should just roll into that gap 7 inches off the ground. And then, so this geometry, if we rotate this down, it touches the ball just the top of the algae. And if you see this gap here, is way smaller than the actual algae, so it actually compresses it quite a lot, which we found in our testing actually is just fine and it works really well. So we intake that, this pops up in here, and then we pivot this up to the point where it is touching the algae, and then all we do is drive to where we want and then spin this out, and we're scored. So the other mechanism we did, if I grab this coral, we designed a little finger prong that can just accept the coral just like that, drive up to it off the ground, spin this, then this pivots up to whatever angle you want to drive with, then we come to the reef, put it in L1, it just plops right into L1, and it's an easy way to just pick up those coral that might drop onto the ground, or the 3 that start on the ground. And then if you want to talk about more of the in-depth how this all moves, do that.
Yeah, so there's this new 550 with a belt loop, and that spins this intake motor. And then we have another 550 back here to pivot the arm. It's at a 81 to 1-ish ratio with.
It's actually at 81 times 3, which is like it's about a 240 to 1 ratio is what we ended up with. We initially had just the 81 to 1, and we decided we probably need more, which was the right decision. And now we have plenty of control over it.
Works perfectly. And then we have this ramp, which looks a bit funky, but there's some method to the madness. One of our ideas was when we knock the algae off from the reef, if we can have it fall down into the robot, that'd be great. And so these polycarb sheets are great at just absorbing the energy of the ball and just stays there. And we have some trails on the sides so the ball doesn't fall out. And then we have the elevator mechanism in the back so that the ball doesn't go out the back.
And another thing that initially we messed up, if you want to come look at this. Initially, we had some problems with these gears meshing, and then so it was just like all the force out here was just bending the shaft. So we had to jerry-rig this plate to pull these together, and now, as you can see, it just works very well. But earlier, when we did that, it was just skipping the gears. And yeah, that's pretty much the intake subsystem.
All right, we're looking at our lifter mechanism here. This is
designed around several pieces of aluminum tubing here. It's a 2-stage lifter, and it works such that it works off of lead screws, which I would not recommend. Don't do what we did here. So it works off of 2 lead screws here. There's one that powers this stage here. The lead screw is inside of this. It interfaces with this motor right here via a gearbox and a little threaded insert for this 1x1 tube, such that it can raise this second stage here. And this design worked pretty well, and it allows us to interface with our climber up there. And then the first stage runs off of a motor hidden underneath the frame here and coming up through here, through this lead screw right in the middle of this, and that goes through a little plate attached to our previous part. The 1x1 tube slides through this set of bearing here, these sets of flanged bearings here, so that it's held in place in both dimensions pretty well, with pretty good tolerances. One thing we failed to account for in our design, because we only had 3 days to work with it, is that this cannot take any upward force before it slides this coupler out. So if you were going to do this, you'd want to add some sort of a bearing plate or some better mechanism to that. We also floated the idea of using nylock nuts as our ends for our lead screws so that we could adapt to them, because those wouldn't move when we need to, whereas these are just kind of haphazardly glued in. And I think I'll pass it off here to our end effector.
Yeah, so on the very top of this 1x1 tube, at the top of the second stage, we have an end effector mechanism. It's 2 motors. One is mounted as a pitch motor, so it's able, when it spins, it pitches this whole arm up and down. This is oriented the way that it is so that we can start the match with the end effector facing all the way back, so it's within the bounds of the robot. Alternatively, it's able to not only pick up at a 45-degree angle and then drop at a negative 45-degree angle, but on the very top rung, what it's able to do is it's able to pitch upwards and then sleeve it over, and then we use the elevator mechanism to pull it down. This is what allows us to score on the 4th rung, which is pretty unique compared to the other rungs since the 4th rung is vertical. Secondly, there's a wheel on here. So this intake mechanism is very similar to the one used on the intake for the algae from the floor, except it's scaled down because it's only used for coral. So in essence, this wheel spins when it's at this angle, and this will pick up from the station. In essence, this wheel will spin, and it'll accept the coral like this. We have a pretty big gear reduction on here. I believe it's 70 to 1, 70 or 10 to 1. I'm not sure. And then that gear reduction keeps the torque very high. So when this motor spins, which it's a Neo 550, it's able to keep the coral in place while we're moving around, and maybe if it gets hit, it'll still stay where it is. Another reason we chose this design is because when there's algae on the reef, we plan on using this mechanism, this end effector, to kind of knock that algae off to make space for the coral. So one thing we were thinking of, doing that, is spinning the wheel in the opposite direction, so that when the wheel contacts the algae, it kind of spins it up and throws it out. In order to kind of help with that, there's these 2 bars that are going along the side of the mechanism, and they kind of go up above all the other pieces of hardware. This is so that when the algae gets taken off of the coral, it rides along these bars and has a smooth transition into the intake of the robot. This is kind of an idea we were playing with, where once that algae was taken off of the reef, it would go straight into our intake and could be deposited directly into the processor. So that's what these 2 guide bars are for. And then also, they're pretty thematic, Poseidon and all. It's a trident. But yeah, so in terms of how everything is mounted, there's a Neo 550 with a 70 to 1 that has 2 plates on the inside right here. These plates are bolted to this 1x1 tube. And then we kind of use that same mechanism on the other side too. We have the Neo 550, the second Neo 550, all the way back and then belted up to the front. And then on the top we have these two bolts that hold these two bars in place, which go from the inside of the 1x1. And that's the end effector.
All right, and now onto the climber. So, as Alex mentioned earlier, when we started our robot design, we chose between two archetypes, and this archetype initially didn't have a climb plan for sure. But as we were designing each component, we tried to figure out where we could fit a climber in to the rest of the mechanism. So the climber ended up being sort of a stretch goal for our overall design. Went through a couple of different ideas. What we came up with that was kind of our best idea was this hook design. So if you want to come in here, we can look at it. We didn't have quite enough time to actually mount it, so it's currently just taped on. And you can see it's kind of loose. But basically, this hook would wrap around the bottom plate on the cage, and then we can just lower the lift down to try to lift the whole robot up onto a shallow climb. This wouldn't be capable of doing a deep climb because we thought that was going to be way out of scope for our robot design. But yeah, so this is basically, we tried to get a simple mechanism that could be added on to what we already had to get those extra climb points. But as I said earlier, this whole robot design was kind of focusing on getting the coral and the algae because that has more point potential over the whole match.
Okay, I'm going to talk about our drivetrain and our electronics system. Big difference in our drivetrain for this year is all the past years we've done a tank drive where we've had two motors going into a gearbox that was then belt fed to a tank drive on both sides. This year, because of the lack of defense availability and you mostly staying on your side of the field, we decided to go for the higher mobility of Mecanum wheels. Obviously, Swerve would give you like bull grip and better, but we didn't have the time to do Swerve in this, so we just had Mecanum wheels that do. So we have more mobility. With that being said, we have one motor for each wheel and they're directly driven. So our drivetrain is made up of 4 Neo Rev motors with a Versaplanetary gearbox going directly to them. Otherwise, moving on to the electronics system, as you've kind of seen throughout the whole system, we have been using mainly Neo motors, so Neo motors and the Neo 550s, and then along with those, we have a bunch of Spark Max motor controllers. The cables are kind of a mess here, and as you might have seen in other parts of the video, we didn't exactly plan too much where we were going to put some of these motor controllers. So this climber has turned into a motor controller mount for this second stage of the motor. But one of those things that was just, we could place it near wherever the motor was. With the Spark Maxes, you have to have the encoder cables being connected to the Neos for the Neos to run. If the encoder cable is not connected, it won't work. So you need to have these controllers as close to the motors as you can get them. Otherwise, it's a basic setup. We do have the new radio on here that's powered via power over Ethernet. And we do have an Orange Pi down in here that does some vision processing that software will talk about more later. We actually have a buck converter taking the 12 volts off of the power hub, converting it down to a 5 volt and powering that off of a USB-C. But otherwise, that's it for the electronics.
All right, so us three are going to talk about the software side of our R3D robot. So I'll start things off by just mentioning that all of our code is available on GitHub. And the link to our GitHub is in the Chief Delphi thread and hopefully will be in the description of this video as well. So if you want to see all the details of the code, you can look on our GitHub repository. But we'll give you a brief rundown here of what we've been working on. So I'll talk about the drivetrain code. So as Peter mentioned, we used Mecanum Drive this year, which is different than what we've done in past years. So we had to rewrite our code a bit for that. And we have both robot relative and field relative driving options. So we're using a NavX gyroscope on the robot to allow for field-oriented driving. And then we've also been working on some other features such as Mecanum Drive odometry and path planning, which will be talked about more later. And yeah, that's the drivetrain.
So there are 2 different pieces that you need to manipulate in this. When we have 2 different intakes for those. We have the intake that will intake both the algae and the coral, with its spike and rollers, and then we have an elevator sort of intake thing that will only intake coral from the player station. And this is a lot of moving parts that the driver will have to keep track of. So part of coding these subsystems is to make that as easy as possible. So we automated having certain positions to automatically do things. Like if you want to intake an algae, all you do is press one button, the wheels will go down into the intake position, and as soon as it takes up a ball, the wheels will go up and it will hold the ball into the hopper. There are also set positions for the elevator, so that way you can automatically bring the elevator to each point on the coral, so that way you can score at each point automatically with just the press of a button.
Alright, and then with Pathfinder, one of the first things that we had to put together was the odometry. That way we could keep track of where we are. And with that, combined with Pathfinder, we were able to draw up some paths to be able to create some more dynamic autos. Just because of the nature of R3D, we weren't able to get a lot of testing done just because we didn't have a lot of the mechanisms kind of like mounted, so we couldn't test all of our like named commands and everything like that. But we did get the actual path fallen working for the Mechanum drive, and so that was fine. And then we also have April tags, or we have April tag tracking on here. And so on our Orange Pi, we are running photon vision, and so we have our camera mounted up here, which preferably, if we were able to move it or find a better place to mount it, it would be facing this way. And the purpose of that is primarily one of the cool features that we had was a kind of auto alignment. That way, whenever you end up in front of an April tag, the robot would correct its rotation to line up parallel to the wreath. That way, it would be much more easy to score. In addition to that, we also had the code to add the 3D April tag processing for updating our odometry as well, and we never got around to really getting to implement that or to really test it in a full-size field, just because of just limitations of being able to kind of test with the full robot. But the code for that exists, and the idea with that is that during autos you would be able to increase your accuracy because you're more aware of where you are in the field, as well as just being able to use that information generally throughout teleop. So I hope that concludes it.
All right, and just to wrap things up, I'd like to mention that not all the design iterations we went through for each of these subsystems were thoroughly covered in this Behind the Bot. If you want to get some more details of that, take a look at our other day 1 through 3 update videos posted to our YouTube channel, UMN Robotics. There you can find some of the other neat ideas that we tried and ended up going away from, like just a finger system to go up and down to hold the coral in the top, as well as the original idea for the robot was to pass algae through the robot until we tried some intake testing and realized this would work. So further details, you should take a look at those videos / our notes from our Chief Delphi thread. And then also, as Anthony mentioned, our code is publicly available. Should be linked in the Chief Delphi thread and below this YouTube video, as well as our robot CAD. This year we have an extensive robot CAD ready. Not every single component, I would like to warn you that it will be available in this CAD. Like some of the brackets might be missing, or there might be some details about electronics or motor placements that might be a little confusing, and you feel free to ask us any questions in our Chief Delphi thread or the YouTube comments if you're confused about any part. But you can find that also linked in our Chief Delphi thread and below the YouTube video. So thank you very much for watching our Behind the Bot season video, and I hope you have a great season.